Good afternoon, everyone. Myself, Camelia Jana. I am working with Professor Santaprasad. The title of my talk is Estimation of Mass Outflow Rates from Magnetized Accretion Disk Around Rotating Black Holes. So, this is the overview. Let's start the introduction. So, we all know that black hole has a very strong gravitational pull. Anything that crosses the event horizon will never come back. In spite of this strong gravitational pull, it has been observed that a highly collimated matter with relativistic speed comes out from the black hole system, which we call as the jet or the outflow. It is very commonly observed in AGNs and X-ray binaries. But the physical mechanism behind this jet generation and its power processes are still not clear. Now, black hole doesn't have any hard surfaces or any boundary or anything intrinsic which can generate the jet. So, if jet has to originate, it has to originate from the accretion disk itself. So, this is the artistic picture of the disk jet system. At the center, there is black hole, and around the black hole, this is the accretion disk. This is the companion star from which mass is being fed into the system, and this is the highly collimated jet. Now, observation also supports that jet does has dependency on the different state of the accretion disk. Like in the hard state, we get steady continuous jet, and during the transition from the hard to soft state, transient ejection is observed, and in the soft state there is no jet activity. So first we need to study the accretion physics to understand the primary mechanism in the accretion which may be responsible for the generation of the jets. In Blandford-Jennett mechanism and in Blandford-Payne mechanism, they have shown how magnetic field can power the jet. So if we want to understand the ejection mechanism fully, the magnetic field is very important to understand. Now, in Radhika and Nandi, in their paper, they reported that no QPO was detected during the jet ejection. Now, this was explained in a way that the inner part of the disc or the corona, which was responsible for the QPO, that was evacuated as a jet, and that's why during the jet ejection, no QPO was detected. So that's mean corona and outflow, they are strongly connected. So if we want to understand the jet generation mechanism, we must study the accretion, the corona, and we must incorporate magnetic field in our theory. So let's quickly review the physics of the accretion. Accretion means accumulation. So black hole has a very strong gravity, and because of that matter will start to accrete towards it. Now matter has some angular momentum, so it cannot directly fall on the black hole. Rather, it will make a spiral motion, make a disc-like structure, and finally fall on the black hole. Now when matter will starts to accrete inward, it has to lose angular momentum. For that, viscosity will help in angular momentum transportation. We all know that at the outer edge of the disk, the matter has almost negligible speed, and when it crosses the event horizon, its speed is near to velocity of light. To satisfy these two boundary conditions, black hole solutions has to be transonic in nature, and the point it changing its nature from the subsonic to supersonic is called the sonic point. Now, depending on the initial flow energy and angular momentum, a solution can have multiple sonic points, and for that cases we can get shock. So what is shock? During the accretion, the rotating matters feel centrifugal barrier which can trigger a discontinuous transition in the flow from the supersonic branch to subsonic branch, which we call as the shock transition. And because of this shock transition, matter will start to pile up and the disk will look like a torus-like structure. So due to this shock compression, the post-shock region becomes very hot and dense, which apparently behaves like corona. We call it as post-shock corona or the PSC. And because of the shock transition, the entropy of the system increases. That's why the shock continuous solutions are always thermodynamically more favorable solutions. Now, as I said, because of this shock compression, the post-shock corona becomes very hot. This excess thermal gradient force at the PSC, this can drive a part of the infalling matter in the vertical direction as a bipolar outflow. So this is the schematic diagram of the disk jet system. The matter is coming from the outer edge towards the black hole. Then it makes the shock transition. This is the PSC. From the PSC, a fraction of matter is going out as the outflow, and from simulation it has been observed that this outflow will always be guided by the two walls. One is called the funnel wall and another is called the centrifugal barrier. So here we are going to study the shock-induced accretion ejection mechanism, and the main aim of my work is to see the effect of the magnetic field in this ejection mechanism. So here we will solve the governing equation for accretion and outflow both, and then we will connect them by the shock conditions. So we consider axisymmetric disk jet system around the rotating black hole in the steady state condition. We take only the toroidal component in our studies, and to see how the magnetic field is affecting our theory. So we introduce this. We will see by this plasma beta parameter, which is defined as the ratio of the gas pressure to the magnetic pressure. So this is the radial momentum equation. This is the mass conservation equation. This shows how the angular momentum will be transferred. And the fourth one is the entropy generation equation. The Q minus term, it is the cooling term. Here we are considering the synchrotron cooling as the main cooling mechanism. And the fifth one is this is the toroidal magnetic flux. So according to ideal MHD, this should be conserved, but in the simulation it has been observed that it varies as 1 by x. So here we take a parametric equations. X injection is the outer edge of the disk, and phi injection is the magnetic flux at the outer edge. So this is the parametric equation. So we are solving this phi equation to solve the accretion flow. Now this is the outflow governing equation. This J stands for the Z component. Now this is the energy conservation and this is the mass conservation equation. As J's are highly collimated, so we do not consider differential rotation there, so we neglect the viscosity there. And also as we are taking only V5 component and J's are going out along the vertical direction, so we are neglecting the effect of V5 during the solving of the outflow equations. Okay, so these are the two equations we will solve, and as I said, this outflow will be guided by the two boundary. The centrifugal barrier is defined from the competition between the centrifugal force and the gravitational force, and funnel wall is where the effective potential vanishes. So this is the numerically calculated outflow geometry. This is the funnel wall, this is the centrifugal barrier, and this middle line shows the jet line. So these are the four shock conditions which has to satisfy during this shock jump. And now we are considering that from the post-shock region mass is going out, so outflow will have the same energy, angular momentum and the density that post-shock region will have. Once we calculate the outflow rate, that is the ratio of the mass outflow flux by mass inflow flux, then from then that we can calculate actually jet kinetic power. So this is the global solution of inflow-outflow. The left one is showing the accretion solution and the right one is showing the outflow solution. So first from the outer edge, the flow will move towards the black hole. First it crosses the outer sonic point, becomes supersonic, then it will make this shock transition, it will become subsonic again, and then it will again starts to gain velocity and cross the inner sonic point, become supersonic, and finally fall on the black hole. Sorry. And this is the outflow solution. From the shock, it is moving away from the black hole, it will cross the sonic point, it will become supersonic, and it will go away. Next, we have fixed all our flow parameters at the inner critical point, and we want to see how our outflow rate will change with the beta parameter. So we can see that for a particular mass accretion rate, if we increase the beta, at inner critical point, outflow rate decreases. So if we increase the beta, that means plasma, that means the magnetic activity will decrease. Because of that, flow will decrease, flow will lose energy. So at the shock, the energy will be less, and because of which the matter which will be ejected from the shock, that will be less. Now for a particular beta, if we increase the mass accretion rate, we can see the RM dot increases. So if we increase the mass accretion rate, flow will have more energy, and as flow will have more energy, shock will move away from the black hole horizon. So the area of the post-shock region will increase. So from that, Posterior region, the outflow is going out, so that's why as the region increases, outflow will increases. So basically, whether the energy at shock is increasing or decreasing. If the energy at shock increases, outflow rate will increase. If it decreases, the outflow rate will decrease. Next, we have plotted the outflow rate with beta for two different value of viscosity parameter alpha. And we can see that if we increase the alpha, flow will lose energy. If we increase the viscosity, flow will lose energy, and that's why outflow rate decreases if we increase alpha. Next, what we have done, we have fixed the beta value and we have varied the energy and angular momentum freely to get what will be the possible maximum outflow rate corresponding to a particular spin parameter. And we can see that for a particular beta value, if we increase the spin parameter, the maximum possible outflow rate will increase. And for a particular spin value, if we decrease the beta parameter, that means if we increase the magnetic activity in the system, the outflow rate will increase. So this study that means says that the magnetic activity is helping in jet launching process. Next, we have plotted the corresponding maximum jet power we can get, and the value or the order which we get is a very good agreement with the observation. So that's all. So finally, I will conclude my talk. So basically, here we have studied the ejection mechanism from a magnetized accretion disk with synchrotron cooling as a main cooling mechanism around the rotating black hole, and we find that if we increase the magnetic activity, our outflow rate increases. Also, outflow rate strongly depends on the mass accretion rate and the viscosity. Next, we calculate the maximum possible outflow rate for the entire range of the black hole spin, and finally calculate what will be the maximum jet kinetic power from our model. So these are the some references. Thank you.
Thank you so much, Camelia. So the session is open for questions or discussions, if any.
Okay.
Yeah,
one question.
We have one question.
Hi, Camelia. So I have one
Yes.
question. In the beginning of the slide, you said there is no QPO when no, there was one reference stating that there is no QPO
Yes.
when there is jet ejection. Is that so for all the wavelength ranges you are considering, or only a small only for a small range of electromagnetic spectrum? Is it true for all the wavelength range?
Okay, that I'm not sure about. So in their paper, what they shown that in the heart state, first the QPO frequency was increasing when it is moving from heart state to heart intermediate, but when the during the jet ejection, they found there was no QPO suddenly.
Okay, I'm asking this because there are in many of the ASEANs there are jets, relativistic jets. They do eject and 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 whether no QPOs are detected for those radio galaxies. I just want to. I was just wondering. Okay. 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 Thank you.
Okay.
Is there any other question? Okay, thank you, Camelia. There is no more question. And we are moving forward to the next talk. H.C. Mehdi. Next speaker. H.C. Mehdi. Next speaker, H.C. Mehdi, present.